Hello and welcome back to 5G System Architecture and Applications. This lesson introduces use cases and applications. We'll be covering the following lectures: 5G diverse applications and use cases, machine-type communications, and final remarks and conclusions. I'll be starting with 5G diverse applications and use cases. 5G applications. As we've seen already in this course, 5G has the capability to support fundamentally new consumer applications, vertical industries, and new emerging business models in this information and communication technology. 5G is expected to be used by various industry vertical sectors. To name some, we have manufacturing, financial markets, healthcare, energy, public safety, and transportation. Some examples of some 5G specific applications include autonomous vehicles and trains, smart grids, smart cities, sports stadiums, virtual reality and augmented reality, airport control systems, disaster recovery and emergency, and remote healthcare. Applications and use cases of 5G, as we can see, are diverse and varied in terms of type, but can generally be classified, as illustrated in the figure, into two main types. The first is human-centric, and the second is machine-centric. However, machine-centric application is quite diverse in terms of applications and requirements, and they're classified into two main types. Therefore, the main use cases in 5G are three: one in human-centric and two machine-centric. So these three use cases are the evolved broadband, eMBB, the ultra-reliable low-latency communication, URLLC, and massive machine-type communication, mMTC. 5G use cases. The requirement for these three use cases are diverse and may need different sets of system configuration. 5G New Radio is quite flexible and can be configured to support these services. 5G Core Network is service-based, and such architecture enables operators to support diverse use cases. Network slicing, dual connectivity, and multi-access edge computing are perfect enablers to support these cases. 5G is also expected to play a role in fixed wireless access, FWA, to provide fiber-like services and penetrate the fixed line services. Gigabits per second, ultra-high-speed BB, as a for-use case, is possible through the use of millimeter wave, SDN, NFV, and MEC. eMBB. Let's turn our attention to the first use cases, which is the eMBB. eMBB, as a human-centric use case, is a natural extension to the existing 4G LTE that will provide a distinctly different user experience than the current mobile broadband services. It is driven by applications requiring much more than what current 4G provides. However, 5G eMBB calls for even more stringent requirements to enhance user experience and goes beyond broadband experience to include the following requirements. First, it must be available in high-density areas, such as conference centers and sports stadiums. 2, should provide enhanced and consistent connectivity everywhere. 3, should support high-speed mobility scenarios, such as high-speed train and even an airplane. And 4, should support QoS that exceeds that of fixed wireless access. In order to meet the above requirements, 5G network is expected to deliver the following. First, the 4 millisecond target for user plane latency for both uplink and downlink. 2, 20 gigabits per second target peak rate for downlink and 10 gigabits per second target for uplink. 3, up to 500 kilometers per hour mobility in high-speed trains with a delivery of 0.45 bits per second per hertz at a top speed. 4, up to 1,000 kilometers per hour mobility support in airplanes. 5, actual user experience data rate of 100 megabits per second for downlink and 50 megabits per second for uplink in urban or suburban areas, and 1 to 4 gigabits per second in hotspot areas. 6. Traffic capacity of 10 megabits per second per meter squared in hotspot areas. And finally 7. 30 bits per second per hertz peak spectral efficiency for downlink and 15 bits per second per hertz for uplink. Potential applications include virtual gaming, virtual and augmented reality, and ultra-high definition video streaming. Let's for a moment consider this picture of a soccer game in fully packed stadium with tens of thousands of fans. Imagine those thousands of fans broadcasting live videos that are synchronized with the gameplay on the ground. There is no way for a 4G system to deliver the expected experience, considering what kind of latency and capacity are required. On the other hand, 5G enabling technologies such as millimeter wave and edge computing may offer the capabilities needed to deliver this experience. Just like having transits located alongside these stadiums to move large numbers of fans in and out quickly, it is expected that 5G operators will bring their services down to these stadiums by deploying multi-access edge computing sites that serve these stadiums. Let's not forget that most of these stadiums and conference centers will also undergo major redesign using mMTC, in lot with the deployment of thousands of 5G-enabled sensors that require 5G connectivity as well. Use cases network requirements. Before we go through the other two use cases, let's review network requirements for the three cases. We have seen this diagram before, which subdivides the 5G network into 4 zones. The first zone is the cell site zone, with latency less than 1 millisecond. The second is 1 to 5 milliseconds, the third 5 to 10 milliseconds, and the fourth, which represents the cloud central zone, has greater than 10 milliseconds latency. Most eMBB use case applications can be served in the MEC zone with 5 to 10 milliseconds. In this zone, one instance of the UPF are deployed. A UPF is connected to external data apps over the N6 interface. Massive data transfer between users and the network may be needed, and a UPF close to the edge is essential. Some eMBB applications may even need to be served by the first MEC zone, where latency is in the range of 1 to 5 milliseconds. Examples of such applications are sports centers or stadiums like the one we have discussed before. Network requirements as suggested by IMT 2020, as mentioned before, call for 20 gigabits per second downlink data rate and 10 gigabits per second uplink. In terms of real experience, it calls for 100 megabits per second downlink and 50 megabits per second uplink. URLLC use cases cannot tolerate high latency and need to be accommodated very close to the cell site to achieve 1 millisecond user plane latency. Another important factor for URLLC is reliability, and the suggested figure is 1 times 10 to the power of negative 5 success in 1 millisecond. High bandwidth may not be critical for these applications, and an instance of UPF may not be essential. The last case, the mMTC, has mixed requirements depending on the specific application, and can be deployed in any of the 2 MEC zones or even the Cloud Central. The most important requirement for this use case is the support of connection density, where the suggested recommendation calls for 1 million devices per square kilometer. Thank you.